a quick recap of what we did in the last class. We looked at or we derived the frequency reversal theorem. In connection with the operation of linear periodically time varying systems, and the result that we derived yesterday was the following. If you have a network N which is LPTV at Fs, and we excite it at port 1 with a current e to the j 2 pi f t, and measure the strength of the voltage at the output at a frequency h sub m j 2 pi f times e to the j 2 pi f plus m f s times t. You will get the same transfer function if you formed the adjoint, which is n hat, and you excite the adjoint with a tone e to the j 2 pi f plus m f s times t, and measure the voltage at port 1, and you will get the same h sub m of j 2 pi f times e to the j 2 pi f plus m f s times t. All right. So, equivalently, this is what this is saying. If you this is the forward transmission, for example, since the input is a current and the output is a voltage, you can think of this as Z 2 1 of m of j 2 pi f, and this is nothing but Z hat of 1 2 of minus m of j 2 pi f plus m f s, right. And what these if n hat is chosen to be the adjoint, then these two quantities are equal, right, which is also equivalent to saying Z 2 1 minus m of j 2 pi f plus m f s is the same as Z hat 1 2 of m of j 2 pi f. These two are equal, and maybe these two are equal. Okay. And it's often very useful to see this as a picture rather than words. So, let us say this is f plus f s, this is f plus 2 f s, f plus 3 f s, f plus 4 f s, and so on. This is f minus f s, f minus 2 f s, f minus 3 f s, and so on, right. And this is, let us say this is the original network N, and this is the adjoint network. Let me copy and paste this. this is n hat. So, what this is saying is that the transfer function from f to f in the original network is the same as that in the adjoint, right. You still remember that the ports are interchanged. Okay. The transfer function from f minus 2 f s to f is the same as the transfer function from f to f minus 2 f s, from f minus 3 f s to f is the same as the transfer function from f to f minus 3 f s, and right. So, this is in general, this is h sub, this is h minus 4 of j 2 pi f plus 4 f s, right, and this is also going to be the same, this actually is h hat 4 of j 2 pi f, and because n hat is the adjoint network, it is turns out to be exactly equal to h minus 4 j 2 pi of f plus 4 f s, all right. So, if we wanted to find the contribution from multiple from a of a single source to an output frequency at f, you would have to calculate the strength of all these guys, right, 1, 2, 3, 4, 5, I mean in this case 8 transfer functions, right, and that would basically, if you did this by superposition, you would do it one source at a time. Now, what are we doing in the adjoint? You just basically apply f, and in one shot you get all these transfer functions in one shot without any sweat, or rather with lesser amount of sweat than you would need otherwise. Excellent. So, the next thing that I would like to draw your attention to is you know the which I find useful is reciprocity, or let me say inter-reciprocal signal flow graphs. And it turns out, I mean, a lot of times, you know, when we are working with these networks, I mean, you often encounter signal flow graphs, and you know, and just like how in a network it's useful to figure out, you know, I mean, it is useful to understand reciprocity because it allows us to find multiple transfer functions at the same time, or transfer functions from multiple frequencies to the same output frequency in one shot. Likewise, you know, it's, you know, the same thing happens when signal flow graphs. And let me just take a typical signal flow graph that we've already seen so far, and that is the Zadeh expansion. So, remember that any LPTV system from input to output transfer function can be basically mapped to this signal flow graph. So, this is h of j 2 pi f, this is and there is a whole bunch of stuff there. This is h sub k of j 2 pi f, or we have always been doing h minus k. So, and this is multiplied by e to the minus j 2 pi k f s times t e to the j 2 pi k f s times t. Right. So, this is x of t and this is y of t, right. This is an example signal flow graph, all right. So, let us kind of see what all elements you find in a signal flow graph, and then we will figure out how to create an interreciprocal signal flow graph. So, what all do we see? The first thing that we see is this, right. So, this is what is called a peak off point, all right. And what is, what is happening? Well, an input signal is coming here and branching out into 3. The outputs of each of these branches is exactly the same as the input, right. It's also possible that each of these branches has got can also have some gain, right. And this is a branch. Let me see. This is a branch with a let me say, actually let's assume that we are working in the frequency domain. Everything is you just put e to the j 2 pi f t and then you get some output y of t k h sub k of j 2 pi f e to the j 2 pi f plus k f s times t. So, this is an example of a branch with a time invariant gain, correct, because remember that these h sub k's are all frequency response corresponding to frequency response of filters that are linear and time invariant. Okay. This branch represents a block with a time varying gain or periodically time varying gain, correct. And finally, we have this, which is nothing but a summing node. Yeah. So, to find the interreciprocal graph, the idea is very similar, right. You can write a, there with our networks we wrote network equations, which is a set of linear equations which relate the unknowns to the excitations, and then we found the unknowns. Then we selected which of those unknowns we are interested in, and therefore, G inverse times excitation time, measurement times G inverse times excitation is our output. We transformed it and got the other network. Well, we could do the same thing actually with a signal flow graph, but since we have already seen what we have done with the network, let us try to see if we can use that knowledge to without having to write the equations all over again, right. So, to do that, I am going to think of the signal flow graph, right, as being as everything being voltages, right. So, the input is a voltage, and if you want to generate 3 copies of the input voltage, what would you do? Yeah, you have 3 branches, right, and each one of them is a voltage controlled voltage source with So, based on voltage signals. So, this is e to the j 2 pi f t, and this is a V c V s with a gain 1. Right, and so this branch will be h sub minus k of j 2 pi f, right. This will be h sub 0, this is h sub k of j 2 pi f. The output of these is also a voltage, e to the j 2 pi k f s times t. And how do we realize summation in voltage? Well, we have a voltage controlled voltage source like this. Then, so this voltage source is basically let us call this V k, V 0 and V minus k, V 0, V k. So, this is 1 into V minus k. Then we have voltage controlled voltage source, which is basically 1 times V 0, and finally, we have this is 1 times V k, all right, and this is basically y of t, all right. So, everything we have is now basically this for instance represents a voltage controlled voltage source whose gain is varying periodically with time, right. This is a voltage controlled voltage source on the other hand, whose gain is fixed with frequency, it is some h sub k of whatever, right. So, now this is a network with a whole bunch of control sources. So, well, to find the adjoint, all that we need to do is apply our standard rules, right. So, what does this become? We start from the right now. So, this is our n. So, what is n hat? We will, so this is a voltage controlled, each one of them is a voltage controlled voltage source. So, now they become a current controlled current source, except that the controlling and control ports have to be flipped, right. So, what happens? So, therefore, the current controlled current source basically means that we have 3 0 voltage sources. This is now a current y of t, all right. So, this is 0, this is 0 volts, this is 0 volts, and we basically have so the current is y of t. So, this must be y of t. This must also be y of t. And this must also be y of t, all right. And what happens to the gain? Well, hold on, before we do that, let me yeah. So, all right. So, let us go further. Yeah. So, the we have a gain here. This gain is a time varying gain. So, this is a voltage controlled voltage source in N. It must now become a current controlled current source. So, what must its gain be?
Gain has to be like T replaced by minus.
Very good. So, you have to this current y of t basically must be now a current controlled current source. So, I am going to just draw the same multiplier, except say that this is a CCCS, current input, current output. And what must be the key point is to note that the gain must be time reversed. So, this is e to the j 2 pi plus k times Fs times t. Let me lower this a little bit. So, this is going to be e to the j plus 2 pi k Fs times t. And so on. And here you will have e to the minus j 2 pi k Fs times t. All right. Then we had in N we have a voltage controlled voltage source going this way from left to right. So, now what must we have? We must have a current controlled current source. So, this is a CCCS, right, with gain h minus k of j 2 pi f. This is h 0 of j 2 pi f. This is h 0 of j 2 pi f, h sub k of j 2 pi f, all right. And so, the output is a current. So, what should you do as far as the what is the next step? Well, earlier we had VC VSs in this direction, they must now become they must become CCCS, right. So, this is let us call this V minus k hat, sorry I minus k hat. This is I 0 hat and this is I plus k hat, all right. And we have so this is basically I 0 hat plus I minus k hat plus I k hat plus, or I just basically I suppose it is easier to simply write sigma I k hat. Okay. All right. So, now therefore, what has happened here? The same input y. Now, I mean this is n hat. So, how do we interpret this in the signal flow graph? Well, this is a signal y of t. What is happening? Y of t, the same y of t is getting multiplied by yeah. So, basically the same y of t is going to So, this is e to the plus j 2 pi k f s times t, and this goes through a gain which is h minus k of j 2 pi f. This signal goes through h 0 of j 2 pi f. This is e to the minus j 2 pi k f s times t. This goes through h sub k of j 2 pi f. And what are we doing to the outputs of these three guys? We are simply adding all of them up. To get x hat of t. All right. So, this was the original signal flow graph. This is the original signal flow graph and this is the new one, right. So, this is say this was x of t and this is y of t. This is the adjoint signal flow graph on the right. So, what all conclusions can we draw from this? Yeah. So, the pick off point in the original network, in the original signal flow graph, right, and if we had gain here, let us call this G 1, G 2, G 3. This is G 1 times x 1, G 2 times x 2, x 1 and G 3 times x 1. Then what will happen in the adjoint? It simply becomes a weighted summing node. So, this is x 1, this is x 2, this is x 3, they are multiplied by G 1, G 2, G 3 and they become a summing node. The pick off point therefore becomes a summing node. All right. So, what comment can we make about a time invariant gain? So, yeah. So, if in the original signal flow graph it was say some h sub k of j 2 pi f, in the adjoint signal flow graph what should you do? The gain remains the same, but direction must be reversed. Right. Okay. And if you have a time varying or let me say I will make this just g of t a time varying gain, a periodically time varying gain rather. What will happen in that joint?
Time is reversed.
And what?
And direction is also.
The directions are all reversed. So, x of t, this is g of t times x of t, which is y of t. So, what should you do? Well, we should reverse, time reverse the gain control waveform. We plop in y of t on the right. What you get here is y hat, I mean whatever y hat of t, whatever you get is x hat of t, which is nothing but g of minus t times y hat of t. All right. The next thing is to see if we can relate these two signal flow graphs to something that we already know. So, for instance, if we excite the signal flow graph with e to the j 2 pi f t, or let us say let us excite this with e to the j 2 pi f plus m f s times t, right. And let us say I am looking at the output here, right. The output I am interested in the output of the signal flow graph at a frequency f. So, what will that be? Well, if I want this frequency to be f, that can, it must follow that it can only come from a branch where you must, yeah, exactly. It will only come from a branch where it will come from the mth minus mth branch, right. So, that this h minus m. So, the mth branch is how the signal will travel. So, for example, so this will go like this, right, get processed by h minus m of j 2 pi f. So, what will the output be there?
H of minus m j 2 pi f into.
The input frequency is f plus m f s. It goes through a filter whose transfer function is h minus m. So, what will be the output strength of the output tone here? What will be the signal there?
Signal is there f plus m f s only.
Yeah, exactly. So, basically because we are talking about a time invariant one. So, the signal here will be h minus m of j 2 pi f plus m f s times e to the
minus j
e to the
minus j 2 pi
no, it is no minus j here. It will be e to the j 2 pi f plus m f s. Then it is getting multiplied by e to the minus j 2 pi m f s t. So, what will come out here will be h minus m
j 2 pi f plus m f s.
h minus m of j 2 pi f plus m f s times e to the j 2 pi f t. Well, this is something that we know. If you take an LPTV network, the transfer function from an input at f plus m f s to an output at f is simply h minus m of j 2 pi f plus m f s. Now, the question is what will happen in the adjoint, right. What would we expect if we excite the output port of the adjoint with e to the j 2 pi f t? What do we from the signal flow graph, what do we see? I mean, if we are interested in looking at what the strength of this waveform x hat is at f plus m f s, what do we get? How do we through which branch will it go through?
Where the periodical gain is multiplied with e power j 2 pi m f s.
So, it will go through the plus mth branch here. So, what you will see is the signal will go like this. It is first getting frequency translated. So, that will give you e to the j 2 pi f plus m f s times t, and is then processed by a filter whose transfer function is h minus m of j 2 pi f. So, what you get here will simply be h minus m of j 2 pi f plus m f s times
e power j 2 pi.
e to the j 2 pi f plus m f s times t. All right. Okay. All right. So, I mean, this is something that we knew already, right. So, if you take the adjoint, in the adjoint, I mean the transfer function from this h minus m of f plus m f s in the original network
Is map.
is the same as the transfer function from f to f plus m f s in the adjoint signal flow graph, correct. So, this is something that we knew already, I mean, and this you know this is consistent, right. Okay. So, that and this is a useful trick to know, I mean, you know, a lot of times people are dealing with signal flow graphs, and if you are interested in finding multiple transfer functions, this is an easy trick to know.